Well, hello, welcome again to Math 315, Analysis and Topology, and this will be the first video for Chapter 3 or Section 3, which is going to be on the series and summability. So in the previous section, the previous sections, we were concerned with sequences of real numbers. We're now going to change tack a little bit. We're going to turn our attention to what happens when we add up the terms of a sequence and thus obtain a series. That means we're moving from looking at a sequence of numbers with commas in between, A1, A2 and so on, and now we're looking at the corresponding series of what happens when I add up the terms, A1 plus A2 and so on, forever, and we're going to write this in sigma notation as sigma I equals 1 to infinity A sub I. Sometimes we'll use n here, sometimes we'll use k, it doesn't matter, it's just a dummy variable here. Now clearly the sum of a finite series of terms is finite. If I've only got 10 terms and I add them up, well, you get a finite number. So we're interested really here in considering series with an infinite number of generally non-zero terms. The idea of adding up an infinite number of terms caused the ancient Greeks no end of trouble, in fact, and it led to a number of so-called classical paradoxes. For example, suppose we have to walk 1 kilometre. Then to do that, we have to reach halfway. That means we have to walk firstly half a kilometre. Having reached half a kilometre, having got to halfway, then we have to reach half of the remaining distance. So we have to walk a half plus a quarter of a kilometre. And we keep going in this way, and we end up adding up this infinite series, a half plus a quarter plus an eighth forever. And we know that this series, in fact, has a limiting sum of 1. It has to be, because that's the distance we're going to walk. But for the ancient Greeks, in their way of thinking, if you added an infinite number of terms, then you must get infinity. And therefore they argued it was impossible to walk 1 kilometre. Well, of course, this is clearly nonsense, and nowadays we recognise that the series is in fact what you've learned at school as a geometric series. We're going to study those again here, and we know it's got a limiting sum of 1. That is, we say that the series converges to 1. That's the very key word, converges to 1. Now, precisely what that means, we're going to define in a moment, but this is going to be a key word. So the aim of this section is to analyse infinite series, and we wanted to develop tests to decide whether or not a given series converges or not. After all, if I add up 1 plus 2 plus 3 plus 4 plus 5 forever, then I'm not going to get a finite number. That's just going to get bigger and bigger, and we say in the limit it goes to infinity. And we'll say that that series, 1 plus 2 plus 3 plus 4 forever, diverges. Now, the first important comment to make is that we should view an infinite series as the limit of a sequence of partial sums. You may remember in that very first video for this course, I showed you that crazy example where I could make that funny series add up to 4. 1 plus 2 plus 3 plus 4. I made it add up to 4, which of course was nonsense. And the reason that was nonsense is because we didn't carefully define what we meant by an infinite series. And here it's going to be the limit of a sequence of partial sums. That is, if I'm given a sequence A of n of real numbers, then I'm going to define the sequence of partial sums, S sub n, as follows. So S sub 1 is going to be just the first term, S sub 2 is the sum of the first 2 terms, and in general S sub n is the sum of the first n terms. And this quantity here is going to be called the partial sums, the nth partial sum. If this has a limit as n goes to infinity, if this makes sense, if it's got a limit as n goes to infinity, then I'm going to define the infinite series a sub n, n is 1 to infinity, to be the limit of the partial sums. So this term s sub n in the sequence is called the nth partial sum of the series. And that's very important. So to make sense of this, what we do is we add up the first n terms, a finite number of terms, and then we take a limit as n goes to infinity of the partial sums. Now be very careful that you distinguish between the terms series and sequence. A sequence is just a list of numbers with commas in between, and we've already looked at those in some detail. A series is what happens when you add them up, and they do behave very differently. So very important that you clearly distinguish between a series and a sequence, or you will become very confused very quickly. So if this limit of the partial sums exists, then we say that the series converges. And if the limit does not exist, we say that the series diverges. Now in many cases it will diverge off to infinity. That means the sum just keeps getting bigger and bigger the further out we go. But note that a series may in fact be boundedly divergent if this sequence of partial sums is boundedly divergent, or the series may diverge to infinity if Sn goes to infinity as n goes to infinity. A simple example of a boundedly divergent series is this one here. You just take minus 1 plus 1 minus 1 plus 1 forever. And of course the partial sums then, if I just take the first term, I get minus 1. If I take the first two terms, I get 0. You take the first three terms, you get minus 1, and so on. So the partial sums here just oscillate between minus 1 and 0, so they don't add up to anything sensible. It doesn't converge, but it doesn't go off to infinity either. It's an example of a boundedly divergent series. Now, the series you're probably most familiar with, I hope, are, let's correct that typo there, are the geometric series. So you'll be conversant with these geometric series from school, but it's worth going over them here and analysing them carefully. I have got a few typos here. So an infinite geometric series has this form. So it starts off with some number a, and you just keep multiplying by r, so you get ar squared, ar cubed, and you add them all up. And this is called an infinite geometric series. So a is the first term, and we obtain, a lot of typos here I'm afraid, sorry, we obtain each new term by multiplying by r, and that's called the common ratio. If we look at the partial sums, then we can write a plus ar squared plus ar cubed and so on, and we stop at the nth term. Now notice the way we're indexing these. This is r1, this is r to the 1, this is r to the 0, so if I take n terms, I've got to stop at ar to the n minus 1 here. Now the usual method of summing this series, the trick you may have seen at school, is that you multiply both sides of this by r. So I get r times Sn. You multiply this by r, you get ar squared, ar cubed, and this becomes ar to the n. And then I'm going to subtract these two finite series. So these are finite series. I'm allowed to subtract them without anything going wrong. So I'm going to take this one minus this one. So I'm going to get a. Now the ar there will cancel with that ar there. The ar squared will cancel with that ar squared, and all the way will cancel. That cancels with that. But I'm going to get 0 minus ar to the n. So when we subtract them, all that survives is a from this equation and minus ar to the n from this one. Now out of that I can factor an S sub n out of here, so I get 1 minus r s sub n, and I can factor an a out of here, that's a into 1 minus r to the n. And finally then I can divide both sides of this by 1 minus r, provided r is not 1. And we finally then have this formula here, which is our standard formula for the sum of a geometric series. This is one you ought to know. You'll be, if you're going to teach high school, you'll be teaching this, so this is a formula you need to know. So it's a into 1 minus r to the n on 1 minus r. Note that r cannot be 1 in the formula, and if we put r equals 1, then we just simply get a plus a plus a plus a n times, which is na. And in that case, this won't have a limit as n goes to infinity. If we put r as minus 1, then the series is just going to oscillate. We get a minus a plus a minus a and so on. So again, that'll be boundedly divergent. So we're not allowed to have r is plus or minus 1 in the formula. Now, if n, for large n, the absolute value of Rn, that's this term up here in our formula, if this will be large if r is bigger than 1 or less than minus 1, and it'll be small if r is between minus 1 and 1. And in fact, it will go to 0. So if r is between minus 1 and 1, if r is a fraction between minus 1 and 1, then this will have a limit and it will go to 0, and that means the sequence of partial sums will converge, and they'll converge obviously now if and only if absolute value of r is less than 1. And the limiting sum then will be a on 1 minus r. The limiting sum will be a on 1 minus r. Because up here, this is going to go to 0, you'll get a on 1 minus r. And there's your formula for the limiting sum of a geometric series, which I hope you remember from school. Now, just to do an example at this point, I think, so we're going to look at the sum 1 over 3 to the k. So we're going to have a look at this sum 1 over 3 to the k. So what we're going to do firstly is we're going to write out the partial sums, s sub n. So I put k as 1 in, I get a third, I put k as 2 in, I get 1 on 3 squared, and the nth term is 1 on 3 to the n. Now this is a finite series, it's a geometric series, so I can use that formula for the sum of a geometric series. So it's a on into 1 minus, the common ratio is 1/3, we're multiplying each term by a third to get the next one, and there are n terms in here, divided by 1 minus r. Now 1 minus a third is 2/3, so I can times top and bottom by 3, and I get a half into 1 minus 1/3 to the n. So here I've used the GP formula, geometric series formula, that we've just derived and which you should know. Now, when it comes then to the infinite sum, we defined that to be the limit of the partial sums. So that's the limit of the SNs. So I take a limit as n goes to infinity of this expression. So this term here goes to 0, and I just get a half here. And so that's the value of the sum, and we're going to say that this infinite series then converges to a half. So I might just write that in here, so we can say that the sum, k equals 1 to infinity, 1 on 3 to the k, we're going to say converges to a half. That means the more terms we take in this, the closer and closer the sum gets to 1/2. Now, we're going to have a brief look at these things called telescoping series, and some series can be summed using partial fractions. In general, I'll generally give you the partial fraction expansion in these things, but in general you can do your own partial fraction work on this, but often I'll just give you what the partial fraction form is. So the partial sums then, the nth partial sums then turn out to telescope. That is, they cancel out and you just get a bit at the beginning and a bit at the end. And we'll see how that works in an example here. So we're going to begin, I'm going to show that this thing here, 1 over k plus 1, can be written as 1 over k minus 1 over k plus 1. And you can go from here to here using partial fractions, but I'm just going to start off, I'm going to give you what the partial fraction form is. We're then going to write out the terms of the partial sum, that is, we're going to sum 1 on k plus 1, where k goes from 1 to n, and then we're going to show that the partial sums telescope down to give you 1 minus 1 on n plus 1, and then we're going to take a limit of this and we're going to get examine this infinite series here. So here are the calculations for this. Here's the worked solution for this. So first thing is I'm just going to check that first bit. So I'm given 1 over k minus 1 over k plus 1. So I'm going to put these over a common denominator of k times k plus 1. And that's going to give me a k plus 1 minus k on the top when I put it over a common denominator. The k's cancel and I get 1 over k plus 1. So that's the first bit. Now I'm going to get the formula for the nth partial sum. So I'm going to use what we did up here. I'm going to replace this 1 over k plus 1 with 1 over k minus 1 over k plus 1. Simply using that formula that we worked out up here. And now I'm just going to put some numbers in. So put k as 1 in, you get 1 minus a half, plus put k as 2 in, you get 1 over 2 minus 1 over 3. Put k as 3 in, you get 1 over 3 minus 1 over 4, plus dot 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 dot. I'm going to put the last couple in. So I'm going to put k is n minus 1 firstly, to get the last bit. So put k is n minus 1, that gives me 1 over n minus 1 minus 1 over n. And finally put k equals n in, you get 1 over n minus 1 on n plus 1. Now here we see this telescoping, because this term here cancels out with this term cancels out with this one will go out with the next bracket, this one will have gone out with a bracket before, that they cancel out. So the whole thing telescopes in, and you just get the first term, everything else cancelled, minus the last term, and so we get 1 minus 1 on n plus 1. So there's the formula for the nth partial sum, and now I take a limit of that as n becomes very big. So the partial sums, that's the limit of 1 minus 1 on n plus 1, and as n goes to infinity, that's going to 0, so the limit's 1. That tells us then two things. It tells us that this infinite series, sigma 1 over kk plus 1, it converges because the nth partial sum has a limit, and we know what the limit is here, so it converges to 1 in fact. Converges to 1. So that's an example of a telescoping series. There's another one of these in the tutorial problems to have a look at later. Now, in most instances, it's not possible to find the exact value of a convergent series. I mean, most series are not a geometric series and not telescoping series, and so to actually find the exact value to see what it converges to, in terms of the real numbers that we know and love, may be in fact either extremely difficult, if not impossible. So it will simply be sufficient for us to determine whether or not a given infinite series converges or not. In general, we're not going to be that interested in what does it converge to. That's often a very difficult question. And interestingly, in many of the applications of these infinite series to other branches of mathematics, one is often not that interested in what it converges to, but just does it converge. Now, using our definition of limit, we can see that this series of partial sums goes to S, and we can write that using our epsilons. That means given some epsilon bigger than naught, we can find a real number capital N, so that if I go past that point, then the limit of the partial sums minus the partial sums, that's S minus S sub n, is less than epsilon. This is just our limit definition that we've had before. Sn goes to S means given epsilon bigger than naught, eventually the sequence is within epsilon of its limit. Now, what's this S minus Sn look like? Well, those are the partial sums here. So that means this S minus Sn is simply going to be A1 plus A2 forever minus A1 plus A2 up to An, and that's just going to give me An plus 1 plus An plus 2 plus forever. And this bit here is called the tail of the series. It's the tail of the series. So our limit definition is telling us that an infinite series converges if and only if its tail, that's these numbers and some of these numbers, can be made small provided we go far enough. Can be made small for sufficiently large n. And let me do a little example of that, and we'll have a look at sigma 1 over 2 to the n. Now we know this converges, we've seen this series before. This is just a half plus a quarter plus an eighth, and we saw that before. It converges in fact to 1. And we can just check that using our geometric series formula, because this series of course is just 1 half plus 1 on 2 squared plus and so on. So the first term is a half, the common ratio is a half, so using that a over 1 minus r formula, we simply get 1, and that's the S, that's the limit of the partial sums. So the S minus Sn, well, that's going to be the sum, a half plus this sum here, which we know adds up to 1, minus the partial sums, and that's going to give us all these terms here. This is the tail. So this bit here is the tail of the series. Now the point is that we can add up, this series is a geometric series, it's an infinite geometric series, and so we can add this up in fact again using our geometric series formula. Here the first term is 1 over 2 to the n plus 1, that's the first term, and the common ratio is a half. So a over 1 minus r gives me this expression, 1 minus a half's a half, and if you double top and bottom, you simplify, you get 1 over 2 to the n. Now, of course, this tail then, so the tail turns out to be just 1 over 2 to the n, and this can be made as small as we like by taking sufficiently large n. One could be more explicit and put some epsilons and n's in here, but I'm just going to put it in English and say we can make this as small as we like for sufficiently large n. Now, one way of, sort of funny way of thinking about this, it's just an analogy, but it's a useful one, I think. So one way of describing this is to imagine that you held a party, and you go on Facebook and you invite everybody. Not a wise thing to do, but you then have an unlimited number of guests turn up. And the trouble is you've only ordered one pizza. Can you give each person something? Well, the answer is yes. The first person, you give them half a pizza. The next person gets a quarter of a pizza. The next person gets an eighth of a pizza, and so on. And we've just seen that a half plus a quarter plus an eighth and so on converges to 1. And that means everybody gets something, and you don't need any more than one pizza. So that's just a very graphical way of thinking about this. and it will be useful analogy when we come to look at the harmonic series shortly. So I'll finish here at this first recording because it does take you a bit of time to copy in the extra bits, and so I probably won't make these full half hour each time because it gives you some time to slow down and stop and copy things in. So I'll finish this one here and we'll continue in the next recording.